This video is part of a series in which I describe how to implement a simple microcontroller core in System Verilog. In this video, I'll be walking through and explaining the System Verilog code that implements the finite state machine that controls the fetch-execute cycle. We'll see how instructions are retrieved from memory in preparation for execution, and how the finite state machine moves from state to state. Here's the finite state machine. On reset, our core enters the start state, and then on the next cycle it enters the fetch state. Instructions can take 1, 2, 3, or up to 5 cycles to execute, and they proceed through the states in this order. So for example, an instruction that requires 3 cycles will experience the states fetch, exec, and exec2. So the first state of any instruction will always be the fetch, and then we'll proceed along this chain here and at some point go back to the fetch and execute the next instruction. Many instructions only require a single cycle, so we'll just remain in the fetch state. If anything goes wrong, that is, if we encounter an illegal instruction, the state machine will go into the illegal state and it will remain there forever, freezing up the machine. Here's a timing diagram that shows what happens when we execute an instruction. In this example, the instruction requires 3 cycles, so we can see that the finite state machine moves through the states fetch, execute or exec, and then execute 2. And then we go into the fetch cycle for the next instruction. In my diagrams, I show Verilog registers in green, like the state and the program counter, and I show signals that are computed combinationally in blue. And we also see the next state signal, which is computed combinationally, and it is used to load the state register. So on a clock pulse, the state register is always loaded from the value that has been computed and set to the next state. So we see that here we have fetch, and then here we have fetch. Here we have exec, and then that's the state next cycle, and so on. That pattern always follows. We're also showing in this diagram what's happening with the memory. The memory has an address input, and then on the next cycle it produces a byte. It reads a byte from memory, and that is available 1 cycle later, as shown here. And we have a register called instruction save. We will always load the instruction save register from whatever's coming out of the memory whenever we have a fetch cycle. So on every fetch cycle, we always will load the instruction save register on the next cycle. And then we have this instruction. This is the instruction that's currently being executed, or more precisely, the 1-byte opcode of the instruction that's currently being executed. And that is produced combinationally from what comes out of the memory and this instruction save register. Our code is, we'll see that the code is pretty much this. If we're in the fetch state, then this instruction will be just what came out of the memory. Otherwise, we'll use what's stored in the register. And we will always load the instruction save register whenever the state is fetch. We also see that we have to compute on the previous instruction, or I should say the last state of the previous instruction, what to feed into the memory. And so typically that is the program counter, but for branch and call instructions where there's a change in the flow of instructions, we might be feeding something different into the memory. But typically we feed the previous program counter into the memory, and at the same time we always increment the program counter, so you can see that happening here. And so during the instruction that was fetched from address 7, our program counter will contain address 8 for the duration. That is, assuming it's not a branch or a call instruction. In order to understand how the finite state machine works, we're going to be looking at the module named core, which encapsulates the EveCore instruction set architecture. This module is pretty long and complicated, so what I've done here is taken the actual System Verilog code, which is tested and which works, and I've eliminated large portions so that we can hopefully see and understand the overall structure of this module. Let's begin with this enumeration, which defines the various states of the finite state machine, like the start, fetch, exec, exec2, and so on. The module itself takes a number of inputs and outputs. The clock input is used, of course, to load the system Verilog registers. We've also got a single step button, and so this input reflects the value of that button, and we'll use it to execute one cycle at a time. And we've also got a reset signal, which we can use to reset everything and start execution from the beginning again. We have several important system Verilog registers, and the most important one, I guess, is the state register, which contains the state of the finite state machine. We've also got the program counter, and we've got this register which I talked about a second ago called instruction save. There's some other registers that I'm not showing here, the stack pointer and the condition code registers and so on, but I won't be talking about those today. We've also got a number of signals that are computed combinationally. This one, the instruction signal, is probably an important one because it reflects the 8-bit opcode of the instruction that's currently being executed. Now, in every clock cycle, we're going to be loading the state register with the value that's computed in the next state. So on every cycle, we'll need to compute what the next state should be. Generally speaking, we will load the program counter on every cycle, and we compute the value that we're going to be loading into it combinationally, and that's next PC. And usually this is just the old value of the program counter plus 1. But for some instructions on some states, we won't be loading the program counter. We've got this signal called program counter write enable, so we will be loading the program counter if and only if it's high, and it will be high for most of the time. Now we've got some signals to and from the various modules that we've included within the core module, and I'm not going to show all of those signals here. I'll talk about those in a second, the ones that we're interested in. But before I do that, I want to talk about this block here, which executes which controls the clock enable signal. So what we're going to be doing is loading the system Verilog registers on the rising edge of the clock, but we're only going to do it if and only if the clock enable signal is high. So we want to pulse the clock enable signal for one cycle every time we press the single step button, and otherwise we want to leave it low. So that's what's going on here. So we need to remember the previous state of the button so we can detect when it goes from low to high. And so with this always module here, or always construct here, on the rising edge of every clock, we will save the previous state of the single step button. And then here we look and we ask, is the single step button currently being pressed, and was it previously not pressed? If so, we've got a transition and we need to do one step of execution. We need to execute things. So we need to set the clock enable signal to high. But at all other times, we need to set the clock enable to low to freeze execution. So in the situations where we want to run the machine at full speed and not do single stepping, we just change this value to 1. We've also got some things to do when the reset line is high. Basically, we set this thing up. This module, the core module, includes a number of other modules. So we've got an instantiation of the memory module, of the instruction decoder module, of the registers module, which contains the 8-bit registers of the EveCore architecture, and we've got the arithmetic logic unit. Some of these modules contain state, and in particular the memory module and the registers module contain state. So both of these modules have a clock input as well as our clock enable signal. Other modules like the instruction decoder and the ALU are purely combinational and don't have any clock inputs. The instruction decoder will take as input the current instruction that's being executed, and it takes it apart and figures out a number of things and isolates various fields in the instruction. But the thing that we're concerned about today is that it will determine what type of instruction it is. So we have an enumeration with various types for the different instructions. We've got ALU, move immediate, move, load, store, and so on. So for example, we've got one type code for all of the ALU instructions. The memory module takes as input the current address, or an address, that's the memory address in, and on every cycle it reads from that address and returns an 8-bit byte in this memory data out signal. We can also update the memory. We won't be seeing that today, but for that we've got an 8-bit data in, and we've also got a signal to indicate when we want to update the memory. We won't be talking about the registers or the ALU module today, except to say that there are a number of inputs and outputs. Okay, first of all, let's talk about the system Verilog registers. This construct right here will update the system Verilog registers. So on the rising edge of the clock, if the clock enable is high, we'll be updating various registers. If it's a reset, okay, if the reset signal is high, then we will initialize the registers, and in particular, the finite state machine needs to begin in the start state, so we initialize that register. We also initialize the program counter to 0, and we don't really need to initialize the stack, we also initialize the stack pointer to 0 and the instruction save register to 0, but we can kind of ignore those for today. But if the reset signal is not high, then we go ahead and update things. And the state is always changed to be whatever the value of next state is. So the finite state machine will always move from state to state. We will also update the program counter on almost all cycles. And we do that if and only if the write enable signal for the program counter is high, in which case we will update the program counter to whatever value we've computed that it should have next. And we also need to update the instruction save register if the state is fetch state. So whenever we're in the fetch state, we will save whatever is coming out of the memory into the instruction save register. And now moving down, we'll use that instruction save register. So let me talk about this always COM construct here. This just goes to the end of the module. So if I scroll down here, I see it goes down here, and we've got a bunch of stuff, but ultimately we go down to the end of the module. The first thing we do combinationally, as I talked about a second ago, is we set the current instruction signal to be whatever the current instruction is. If we're in the fetch state, then we use whatever is just now coming out of the memory. Otherwise, we will use what came out during the previous fetch state and that was saved in the instruction save register. So this is the code that sets the current instruction, and we don't modify this any other place. Now, the structure of this is basically a big case statement. So we look at what state we're in, and then we ask what kind of instruction do we have. So we see another case statement here, which looks at the type of the current instruction. So remember that the instruction decoder takes as input the current instruction and determines what type of instruction we have. So at this point down here, we'll use that to determine whether we've got, say, an arithmetic logic unit instruction or move immediate instruction, and I've left out a whole bunch of stuff here. So we look at the state, and then we look at the type of instruction. And then we look at the other states as well. So we have the start state here, we have the fetch state, and then we have the other states, exec, exec2, 3, and 4, and so on. We don't have an illegal state. Instead, we just have this default, which covers the illegal state. So whenever we're in the illegal state, we simply stay in the illegal state. And we also don't increment the program counter, so we set the program counter write enabled to 0, so that if for the purposes of debugging we want to look at the program counter and see where we are, we can do that. I like to show in an always COM construct all the variables that I intend to be setting. And there are a bunch of them, a bunch of different control signals. For example, the signals to control the register unit, as well as some other stuff. But we're not going to show those today. But I do want to show the ones that we're really concerned with. And in particular, we have the input address to the memory. And we also have the write enable signal. By default, we'll set it to 0. We won't be writing anything to the memory. For some instructions, like the store instruction, we will change that. But this is the default. And when we do write, we'll generally take data from the register module. But our default for the memory unit is to send the program counter in as the address that we want to fetch from. And the other thing that we have as a default is the next state. It's always the fetch state. So typically we'll go into the fetch state unless we need to go into exec or exec2 or exec3 or the illegal state. So by default we return to the fetch state on the next cycle. And we also increment the program counter. So here we see the next PC being set to PC plus 1, and we raise the program counter write enable signal. So when we're in the start state, we don't really care about what the current instruction is, obviously. We just need to fetch something from memory. So the whole purpose of the start state is to allow the memory time to fetch the first byte, that is the first instruction, which is at address 0 in the memory. So our default for the write enable signal is 1, and for the next state is the fetch. I'm just including that as a comment here. I don't need to actually include the code. When we're in the fetch state, then we do need to look at what kind of instruction we have. And again, I repeat the defaults as a comment here. As this code gets longer, this is a bit helpful to me to kind of remember what the default is. And so let's take a look at, for example, an ALU instruction. Now, I haven't really talked about the register module, but you can see that we are sending whatever comes out of the ALU to the register unit as its data input, and we are raising the write enable signal for the register. So we will be writing to one of the 8-bit registers in the next cycle. And we also have to supply the address of the register, that is, which register we want to be writing to. So this is a 3-bit signal that indicates that we want to write to the A register. I haven't mentioned the Verilog registers for the condition codes, but we also need to update those with the output of the ALU. So we see that signal here. But since we're not modifying next state, we will be going into the fetch state on the next cycle. So the ALU instruction is only a single cycle. On the other hand, the move immediate instruction is an instruction that takes multiple cycles. So you can see that we are setting next state to exec state. Now the move immediate will need to fetch the next byte, which is the byte after the opcode. That's the byte that contains the immediate value that will be loading into a register. So the only purpose of the fetch state for the move immediate is to allow the memory time to fetch the next byte. So we will go ahead and increment the program counter and update it, and we'll fetch it, but we won't be loading the instruction. The instruction will just stay the same. So when we move into the exec state, we can go ahead and do something with that value. Now for the other states, I'm not showing any great detail here. I'm just showing that for each state, we have a case statement, and we look at what kind of an instruction we have. And so we would see code here for the move immediate instruction, even though I'm not showing it in this slide. And the same applies for these other states as well. Okay, that concludes our discussion of the finite state machine and our introduction to the core module. In future videos, I'll go into the various instructions in greater detail, talking about their timing and going over the code for them. But that concludes this video, and I will see you in one of those future videos. Thanks for watching.